Welcome everybody to this colloquium organized by the section of sensory motor control. Jeroen Smeets is the head of the section and would normally be the host, but his son is receiving a master's degree today and Jeroen has asked me to take over. My name is Maarten Wilbert, but more importantly, today's speaker is Professor Luc Selen from the Donders Institute Brain Cognition and Behavior in Nijmegen. And we all, or most of my colleagues, know Luc because some 20 years ago he enrolled in the program of Human Movement Sciences after studying applied physics. And I have to say that he turned out to be one of our best students ever. Under my supervision, he did his master internship on drop jumping, for which he developed a cross-bridge model. And Luc is the only student who I ever gave a 10 for a master internship. So still the best student from that part. After completing his master's, I think it was summa cum laude, right? Luc did his PhD at our faculty under supervision of Jaap van Dien and Peter Beek on the question of whether joint impedance helps to attenuate the effect of neuromuscular noise on movement precision. And as a PhD student, Luc not only performed excellent scientific work, he was also one of the organizers of many social activities and sports activities, such as squash competitions and speed skating outings. Those were the days. Luc is an outstanding speed skater, by the way. In 2007 or 2006, I'm not really sure, after completion of his PhD, Luc successfully applied for a very prestigious postdoc position with Daniel Wolperts, the Department of Engineering at Cambridge University. And 3 years later, in 2010, he got an appointment at the Donders Institute. And he also got a Veni grant from NWO for a project on motor learning. If I understand it correctly, Luc is interested in how humans interact and are able to interact effectively and efficiently with their environment, despite all the uncertainty present in the body and the ever-changing world. And his presentation today is on how to perceive, decide, and act in an uncertain world. I'm very curious, Luc. The floor is yours. You said that during the presentation, there's the opportunity to ask short questions for explanation, or should we reserve those to the end? I think that's up to you.
And if it's really unclear, shout.
All right. And for the people that are in the research master, please chat your name so that I can save the chat and forward the names to Huub, who is the program director. Luc, you have the floor.
Thanks, Maarten, for the kind words. Yep, so I'm gonna, well, as Maarten said, my background is was a little bit of physics and human movement science. So I've done a lot of different projects, and that is still so. I don't have one particular interest. There's always motor involved. But so it's a little bit of 3 projects, but we do many more things, many more topics. I find it hard to focus on one. So how to perceive, decide, and act in an uncertain world. That's what I'm going to talk about. And I work in something called Sensory Motor Lab that I lead together with Peter Medendorp. So my general research question is, how does our brain deal with noise, uncertainty, and ambiguity, both for perception and action? And most of the time, I actually am interested in how these two interact. And although I'm in the Donders Institute, where the brain is the most important organ in our body, and most of the people in this building will say that anything below the neck does not matter. And I was trained by Maarten. I know that that does matter. I do not look at the brain directly. I will always use behavioral studies and or electromyography, computational models. And I think I have 2 or 3 papers where I do use some EEG, but that is really rare that I do that. So I'm going to try to talk about 3 topics. I don't know whether I will make the 3rd one, but the first one is, what is vertical and how do we actually decide what is vertical? The second one is on decision making. So how do you link information from your environment to actions? And the third one is how do you make online corrections during movement? And how do you especially integrate information from different senses at that time? So the vertical is, oh, where's my mouse? Here. The vertical is obviously the spirit level, decision making, and this is something called optimal feedback control, a very influential framework in motor control nowadays, which is the third topic. Okay. So the first one is age-related reweighting of visual and vestibular information or cues for verticality perception. And that's a project of multiple sub-projects where Bart Alberts was the PhD student, Peter co-supervised, and Anouk was at that time a PhD student in our lab, but also in Jeroen Smeets' lab, and Anouk was in part at the VU, but also worked for us. And she's currently in Canada, if I'm correctly informed. Okay, so who knows what this is? It's Villa Volta. I have never been there, although it's 25 years old. And I'm going to try to play this. And I want you to focus on what the mirror does here, because the whole attraction is built to make you perceive the wrong vertical. And it takes a bit, yes. So now it's upright. And what you see now is that the mirror starts turning, but that means that you're being tilted. And at some point, the whole building starts to rotate around you. So the vertical is aligned with the mirror, the true vertical. Yep. So that attraction essentially is the starting point of our research. Well, actually, we did this, and then I discovered that Villa Volta existed. So what I want to try to explain to you is how does our vestibular system combine with our visual system to make a percept of where gravity is. And what we do for that is the following. So the room, the visual room, we call visual context. Then you have your vestibular organ that gives you vestibular information. And I now lump a couple of things together because you have your vestibular organ, but also the distribution of your blood in your body tells you something about what vertical is. Okay. And you have a lot of prior experience. You know that most of the day you sit roughly upright. Okay, that we call prior. And then we do something called Bayesian inference, and we're not going to go through the math, but there is a lot of math behind that. That tells you that the likelihood of being upright has a funny function, but 0 has the highest probability. Your vestibular organ tells you that you have a very sharp vestibular likelihood for being upright at this moment, and you know from prior experiences the rest of your life, what you did all the rest of your life, that you're most of the time upright with some variance on what is also likely. And you somehow combine these in an optimal way, weighting the ones that are very trustworthy very heavily and the ones that are not trustworthy not so heavily, to get a head in space posterior. This is my estimate of what upright is. Okay. So now the question is, how do I in the lab then manipulate the visual context and the vestibular context independently? So what we do is, I changed something last minute. So the question here is that vestibular likelihood, does that change with age? So if a child goes with his grandparent to Villa Volta, who has the best perception of that attraction? And my claim is going to be that the grandparents have a much bigger effect than the grandchildren, right? And the reason for that, I'll explain later in more detail, is that vestibular likelihood becomes worse with age. The idea being that you have more noisy vestibular sensors as you age. But that's pretty hard to show because we do not have a direct measurement of the vestibular organ. For an eye, it's fairly easy to show that it has deteriorated. You just do a reading test and you see how small you can go with the letters. It's a bit harder for the vestibular, but we believe that we have a trick to do it. So, hypothesis: with increasing age, the vestibular system becomes more noisy, and due to the sensory reweighting of the visual context, the influence increases on the perceived vertical. So if you do not trust vestibular, you're going to trust the visual one, but that makes that I can fool you. So how do we do this in the lab? Well, we do not build a complete villa volta. What we do is we take a screen, we present you with a visual context, which is a frame that is rotated. We show that for 250 milliseconds. We flash a line inside that frame, and we ask you to indicate, was that flash rotated clockwise or counterclockwise of your perceived vertical? And we do that a couple of thousand times. A couple of trials. So here you see a square, and that depends on the brightness of your screen. And once I push the button, you will see a line. And my question to you is that rotated clockwise or counterclockwise? Decide for yourself. Here comes 1. Okay, we rotate the frame. 3, 2, 1. Rotate the frame. 3, 2, 1. Okay, one more. Rotate the frame. So, how many were clockwise? How many were counterclockwise? None. They were all upright. But the context pulls you in the direction of the frame. The frame context pulls you in that direction. So we can manipulate how you perceive that vertical line just by adding a frame. So in the lab, we do it in the following way. We present 9 line or rod orientations up to 12 degrees. We do it at 2 head tilt angles, and we just ask the subject to tilt their head 30 degrees while we put a cushion to put their head against. And we have 18 frame orientations. We repeat every combination of these 10 times, so you have more than 3,000 trials. And now what you can do is for every frame and every head orientation, you build a so-called psychometric curve, which I will show you. So here the frame is tilted 20 degrees left. We present you with a line of -12, what is this, -8, 0, and so forth and so on, 9 orientation, 10 repetitions, and we just compute how many times did you say it was clockwise. So if the line is rotated a lot, you're going to always say it's clockwise. If it's rotated in the opposite direction a lot, it's going to be counterclockwise. But what you can see is that if the frame is upright, you have roughly 0 as your point of subjective equality, where you say 50-50. If you rotate to the left, you also pull the point of subjective equality to the left. If you rotate the frame to the right, then you get a rightward shift of the curve. Now, in theory, you should be steepest in this curve if you are upright, if the frame is upright, and you get worse with orientation, with rotating of the frame. That's not so clear in these specific curves. But what I'm now going to do is I'm going to take the points of subjective equality, and I'm going to take the slopes of these curves, and now plot the frame orientation on the x-axis, the systematic error, which is the point of subjective equality, so the crossing here and that crossing, as a function of frame orientation. And what you get is a curve that has 0 error, because if I rotate the frame 45 degrees, then there is no visual context anymore that pulls you anywhere, because it's the same as an upright frame. And the same holds on the other side. In the middle, we have hardly an effect, but here we have a negative effect, here we have a positive effect. Then we look at the variance, which is essentially the slope of this curve, and that's messy, but there may be something where you say, okay, variance is high for extreme frame orientations and lowest for the upright frame orientation. Now, if I do this, this is one subject, and the red dots are the 3 red curves. Now we do it for multiples, for 3 subjects. So we have a young adult, which is a student, an adult, that were the people on my corridor, all the 40ers. We collected these actually after we had these 2, and then we thought, let's do the middle as well. And the elderly are some age match controls for another experiment, but they're all 60 and 70 plus. And so this error and sorry, the green curve and the blue curve and the red curve are fits of this Bayesian integration model. So how do you combine visual, vestibular, and prior information? And what you can clearly see here is that the peak-to-peak bias, which is this from here to here, increases for the elderly, and that the average variability also increases for the elderly. That is single subjects. So one young adult, one adult, and one elderly. Now, if I plot the peak-to-peak modulation of that curve as a function of age, you get a very nice positive correlation. And these were my 3 subjects that I just showed you. Okay? And for the variance, you get something similar. The variance curve, the average variance goes up with age. So this was my elderly control, but there's actually people even worse. This is a model fit. Now, this was the model, and that gave us a curve. But what that model also gives us is a weight on visual, a weight on vestibular, and a weight on prior. And these 3 weights always have to add up to 1 because it's a probability. Now, if you look at the prior weight, that doesn't really change with age. So you do not rely more on previous experiences if you get older. If anything, this line is negative. The vestibular weight goes down. So you trust, or you rely less in your estimate of what is vertical on vestibular as you age in this task. Your visual weight goes up. But that doesn't tell me anything yet about how your sensors are doing. But the model actually has the sensors in there. So here is some uncertainty on your vestibular. These kappas are essentially 1 over sigma for a von Mises distribution. So it's also a variance measure. So these are part of the model. So I can go 1 step further. So we see a vestibular weight decrease. We see a visual weight increase. Now, is that due to the visual system becoming worse or the vestibular system? But the model also tells you something about that. And if you look at that, then you see that the visual noise does not increase with age according to the model. What does increase is the vestibular noise. And that causes that the relative weights between these 2 is going to shift. Okay? So by using a Bayesian optimal integration model, we can work backwards what the noise levels of the different sensors might be. So this is clearly vestibular. Why would that be relevant? Well, this is anecdotal from general practitioners. So oftentimes they have patients that say, "Doctor, I have the impression that I don't see very, very clearly lately." Now, the GP will probably say something like, "Let's test your vision. Stand here 3 meters from the wall, read these letters. Can you go 1 line lower? Can you go 1 line further?" And after the test, the doctor says, "I don't see what the problem is. Your reading abilities are fine." The problem is not in the visual system. The problem is in the vestibular system. And it's really hard to tease that out. There are some tricks to do it, because what we do know is that you can also measure something called dynamic visual acuity. So static visual acuity is you standing in place in front of a wall with letters and you read them. But if I put you on a treadmill and I have you walk at 2, 4, 6 kilometers an hour, then you will see that even young students decline a tiny bit in their reading ability because their VOR is not perfect, so you get blurry vision. Okay? Vestibular ocular reflex. Martin should have explained you that. However, if you use this test and you take, I think there's 57 patients in here. This is a study done in Maastricht by Herman Kingma and friends. It's pretty hard to show that there is a decline in vestibular function with age. That also makes sense because you do not have a very fine-grained measure of that reading ability, because it's just you can go 1 line smaller on the letters. That's the kind of steps in which you can measure. However, this task works really well, the walking task, if you look at bilateral vestibular patients people that do not have that have a dysfunctioning vestibular organ and healthy controls. What you see then is a decrease compared to static visual acuity, a decrease with walking speed for healthy controls. But if you do that with vestibular patients, they essentially are way off. They're much worse. Their reading ability is really bad as soon as they start walking. Now, this looks very much to something that we have shown in also a bilateral vestibular patient group. So what you see here is data from a patient group called DFNA9, and they have a genetic disorder that makes that they will lose their vestibular organ completely by the age of 40, roughly. They also lose their hearing, but for that you have cochlear implants. So we had these patients come over and you don't see anything. They look totally normal. And the first one we had here in the building, I asked like, okay, how did you get here? Well, by car. Do you drive a car? Yes, why do you ask? Well, you do not have a vestibular ocular reflex. Ah, you understand something. These people drive a car, but the gentleman said literally, I avoid the town center. They have cobblestones there, and I dislike that. He doesn't see anything because his vestibular ocular reflex doesn't work. So if we put these people in our experiment, what you get is that they essentially, so here you see the weights of vision, that's the context, and of the vestibular system, and the prior weight. What you see is that the prior weight does not really differ between controls and patients, but that the context weight is way higher for the patient group than the control group. Or if you plot it in a different way, you take the sensor weight and you take the context weight, the patients are all in the top left and the controls are all in the bottom right. So this is another way of showing what was in a previous slide, that bilateral vestibular patients have no VOR. Okay. Now the next step that we want to take, and we haven't done yet, but I work for artificial intelligence in part, so I have some students working on that. What I want to do is actually see whether I can get from 3,000 trials, which takes forever, to, let's say, 100, 150 trials to get these parameters out of the model in a single subject. But that means that I have to make something called closed loop psychometrics, where I actually optimize which stimuli I present to the subject based on what I've done so far. Because if you are at the extremes of a psychometric curve, you do not get any information. You want to be on the slope of the psychometric curve. And that you can do with something called adaptive stimulus presentation. And that has been well established in monkey neurophysiology, but it's pretty tricky. That sounds counterintuitive, but it's pretty tricky to do that on a 7-parameter model in humans. But we'll get there. And the hope is that we can build a clinical test of vestibular function similar to the visual acuity tests that you do at your general practitioner, and that you might even be able to do at home. Okay, that was one. You can shout now, because else I continue. And I don't see the chat anymore. Okay, good. Next. This is old and new. As Maarten said, this is a completely different topic. So I worked for a while with Daniel Wolpert, and at that time, Mike Shatlin, who is at Columbia, he does monkey neurophysiology on decision making. And we try to bring that to the human. And so I'm going to first talk about a study that was a long time ago published, and that we're now following up on by my PhD student, Yvonne Visser. So, if you are a simple animal, and this is plankton, then what happens if these are these animals? If I turn on a light, it's very simple. They all go to the right of the space. And they have something called eyes. and they have ciliary bands, and this is essentially their motor. And essentially they have a direct connection between perception and action. There is no deliberation. They don't think. It's just direct wiring. If we see light, we go there, there must be food. Hopefully our system does not work that way. Although if you read the literature, a lot of people will say that you first decide and then act. And I'm going to claim that you don't, that your actions are being prepared while you're making a decision, and that you can release your action at any time. And the real world example is something like this. Suppose you're approaching a road crossing, then it depends on the people on the sidewalk, how they behave, how ready you are to brake. If there's no one there, you do not even have your foot ready to brake. If there's a lot of stuff going on the sidewalk, you will be more ready. That's what it feels like. But can we show that? One sec. So does the CNS, central nervous system, provide information from the decision process directly into the motor system? Or do we have a very tight watershed? There's something that decides, and only then we tell the motor system to do something. So how do we do that? We have robotic manipulanda, with which we use a lot for motor control research, but now for something else. So you hold the handle of the manipulandum, and in this case, what you see, and I'm going to show you examples of that, you see a patch of randomly moving dots with some having direction. And on one trial, that direction is in the is reflection, and for some that is in the direction of extension. So you sit here in the center, you see these dots, you have a target for flexion, elbow flexion, and you have a target for elbow extension, and the whole hand is on air slats, upside down air hockey, I always call it, to make sure that we can measure EMG. And then what we do is we quickly stretch your biceps. The robot just grabs your arm and pulls you 1 centimeter. That stretch reflex is a readout of the motor system, deep down in the motor system. And that we're going to use as a measure of how prepared your system is for the action that it has not decided about yet. And then you have to indicate what you think the direction of the dots was. What we manipulate is the so-called coherence, that is the number of dots, the percentage of dots that have direction. So for 0% coherence, there's nothing, everything is random. For 12.8, there's only a few dots that are informative, and all the rest is just rubbish. And the other thing we control is how long you're allowed to watch these dots before we give that stretch to your arm, to your biceps muscle. And we take something called an exponential distribution for that to make sure that you cannot predict when that perturbation comes. For the technical people, this is called hazard rate. The chance that it's going to happen in the future is constant over the experiment, over the time. That means that we have a lot of trials with short duration and very few with long duration. Okay, here's a trial. So yellow is the dot where the hand is. Now you're going to see a trace where that hand moves, but the subject doesn't see that in the end. The 3 dots here, there's a 4th one here, is the patch of randomly moving dots, extension target, flexion target. And here you see EMG for the extensor muscle and flexor muscle. Red is the onset of the perturbation, and these vertical lines are some specific time windows, but what matters is that this last line is at 100 milliseconds after perturbation onset. So let's see whether this works. It's used to work. So dots are moving, bang, and you indicate what you do. And I think it's clear for everyone, but I don't know how this works over internet, that the dots are moving in the flexion direction. And this was the easiest trial the subject ever got. So it's quite frustrating in the beginning. But what you see happening is that there is a quick M1, a very short latency reflex here, but also here, before 100 milliseconds, you already see the flexor EMG coming up. Now I show you the opposite. The dots are going in the opposite direction, but it's still loading. Yes. And now suddenly you see there's a tiny blip here, but nothing on the other side. But this is not the voluntary EMG yet. This is really only reflex evoked or perturbation evoked EMG. Okay, so this is the kind of experiment the subject was doing, although he did not see his hand. And you can also see in the yellow trace that the stretch is up to there, and then the rest is voluntary. Okay, good. So let's first see how often do people actually do this correct. So if you watch the dots for longer, you get better. And if I show you dots with more information per unit time, you also get better. So you get these nice plots. Now, then the question is, can we actually build a model of the decision process? And yes, you can. You can build something called a drift diffusion model. And in essence, what you do is you say, at every moment in time, you get a piece of information. And that piece of information is drawn from a Gauss distribution. If there's zero coherence, then on average, you get zero information, but sometimes you get positive, sometimes you get negative, the black one. But if you are in a high coherence condition, then the amount of evidence you get per unit time is shifted to the right, and you hardly ever get counter evidence. But note that for 25%, you every now and then go in the wrong direction. Now, what you do is this is per unit time. So now we're going to generate random walks. Based on this, multiple random walks for the 3 different coherence levels. And you see, we call this the decision variable, that there comes a distribution of the decision variable. So for the highest coherences, you will always make the right decision. But if you are in the lower level of coherences, you sometimes will decide to go in the opposite direction because the evidence is in that direction because of the randomness. And the mean is that coherence level times a constant times time, and the variance is the square root of time. Doesn't really matter for now, but what is important is to remember that we can compute something called decision variable. Based on the decision variable, we can compute how many times were you correct, and then we fiddle with k, we optimize k such that we can predict the correct responses. So if you take 0.2 second of viewing duration, then you see distributions like this. If you go further, and we call this the upper bit above 0, that's going to be the correct choice, and below 0 is going to be wrong choice. And that ratio tells you something about what you should see. And obviously, if we go further in time, these distributions shift, so the probability correct goes up. And if you then manipulate k to optimize these distributions, you can fit actually nicely the data. There's one parameter to fit these curves. Okay. But we evoked reflexes. Now the idea, and this is grabbed from Isaac Kurtz's work, the idea is that this early response, very short after the perturbation onset, is monosynaptic spinal group 1 neurons. So essentially, there is no way that the brain can influence this reflex. But the group 2 and the reticular formation, they are maybe under control of motor areas. So the idea is we're going to see modulation of these long latency reflexes, but not of these early ones. So here is a trial out of the experiment. Everything before 0 is viewing duration, where you were viewing dots. And here we chose trials between 270 and 350 milliseconds. And everything after the perturbation, the dots were off. You have all the information already. And the idea is that you see a difference. This is this monosynaptic response that should not differ between hard and easy trials. But if you go further in time, they should separate, but should separate before the voluntary response. And they do in this case. But now, oh yeah, and if you go for extension evidence, you get something similar, right? Now we're going to quantify, we're going to compute for each and every trial the EMG magnitude in the first window. What was it? 25 to 45 milliseconds after perturbation onset. In the second window, which I will ignore for now. And in the third window, which is 75 to 105 milliseconds. So still very shortly after the perturbation onset. And we compute one number per trial. And now I plot the difference between the extensor and flexor EMG for these time windows. So the first time window, which is this monosynaptic response, there should be no effect of how long you have seen the dots before or the coherence level. And if you do that, indeed, it doesn't matter. Everything stays very close to zero, irrespective of coherence. But if you move to the third window, you might start to see something. And indeed, you see that with time and coherence, the traces start to separate. Now you might say, how can it be that on a 0% coherence, no information trial, you still see the lines separate? Well, there is no correct or wrong in a 0% coherence trial. You did not get any information, so we counted them all as correct, and their choice was what we called correct. So this is the default what you would get, and anything above that is caused by the additional information of coherence. Okay, so yes, the reflexes are modulated. Then the next step, can this relate to the decision variable? So this was the EMG. Now all choices, correct and incorrect. And the decision variable you can also compute, because we had fitted that or computed that based on behavior. That was this. And these look very nicely the same. So now we try to correlate these, well, actually with the Gaussian process, but it doesn't really matter. What you now see is if you correlate the decision variable based on behavior only with the reflex based on EMG, then there's nothing on the monosynaptic reflexes. There is more on the medium latency reflexes, and there is a lot of modulation on the long latency reflex. Note, viewing duration and coherence are two knobs we turn in the experiment, but by computing the decision variable, we can collapse them and actually get rid of one dimension, which makes this analysis easier. So claim, we leak information even before the decision into the motor system. Why would you do that at all? Well, if you look at behavior and you plot decision variable against the distance moved, then you see that 125 milliseconds after perturbation onsets, the higher your decision variable, the further you have moved. And the instruction was react as fast as you can. So you tune this through, probably, to fulfill the requirement of the experiment. You prepare yourself more if we push you to do so. And you do that even though you don't know yet what is going to be correct. You only know what is going to be most likely. Okay. So CNS provides information from the ongoing process to the motor system. The motor system is pre-tuned based on certainty about the upcoming task. The more certain, the more tuning. And pre-tuning results in a faster completion of the task. Okay. So then the next question was, if you tune your system so far, can we then also see signatures of what we call a change of mind? You all know from sports events or from talking with someone that you sometimes are executing an action, and while doing it, you realize this is not a good idea. You prepare a full backhand, and last moment you switch to your forehand, like fumble the racket in front of you. Or something comes out of your mouth and you realize this is not a smart thing to say, and you try to change it on the fly. Can we find signatures of these changes early in the motor system? So what we did is we changed the task, and again, robotic manipulandum, red is the hand. This is your start location, 2 targets, but now you have to make a far reach. But what you can do is mid-reach, sorry, you bring your hand to the start location. There's a yellow dot here. That's actually a simulated pin to make sure that people have to choose at the start. Because what you might do is go through the middle if you don't know yet, just to make the decision process longer. Then we show you dots again. We stretch you. Now we stretch you to manipulate to a stretch over pectoralis. And then you make a movement, and we show you whether you're correct. But, oh, sorry. Targets are placed that you have pectoralis activation. Coherences and duration are optimized to make sure that we get changes of mind. Perturbation is now in the shoulder instead of the biceps. And what you get is that on most trials, people go directly to the target, the dashed lines. But the solid lines are actually changes of mind. You start to the left target, and then midway you think, oh, wait a sec. And we put quite a strict timeout, so you have to be quick. That was impossible in the first task because the two targets were orthogonal, and it's way too costly to make a change of mind. And if you now look at initiation and termination, so initiation is which target are you moving towards at the start of the trial, and where did you actually end up at this termination, then what you see is that termination on average actually works in your favor. So if you make a change of mind, that is most of the time to your benefit. Sometimes you make a change of mind from a good start to a bad end, but most of the time it's a bad start to a good end. Okay. And then you can make these whole reflex patterns again, and we again nicely get from short to long viewing durations that indeed you increase your reflex gains. And if we collapse over all viewing durations and only look at coherences, then the easier tasks result in stronger reflexes. And here only you see the start of the voluntary. But what we're really interested in, which we haven't sorted yet, is what happens in a change of mind. So what I plot you here is, again, this time window after perturbation onset, 100 milliseconds after perturbation onset. That's what we're interested in. And now the solid line is something that started to the left, but changed to the right. Note that this is pectoralis activity, which means that at the beginning, your pectoralis should be active, but to go to the right, you should shut it off. And that's what you do. And we compare that to a trial that's a non-change of mind to the left. So these go up together, and then you see separation happening here. And the same thing we can do for the other side, there it's less clear. These are single trials. So now what we're going to do is we're going to take all the change of mind trials, and we're going to find a non-change of mind trial that had the same viewing duration and the same coherence. And we link these two EMGs and subtract them, because the EMG is by definition already different for the different viewing durations. So we have to find a match. And if you have these matches, you subtract them, and then you plot the average of these subtractions. If you do that, then what you see is that if you make a change of mind from a start to the left, but you end to the right, then you see a massive reduction in EMG activity. Whereas if you make a change of mind from right to left, you see less of a reduction. And that, and I'm not going to go into all the details, is probably an indication that although you had the same information on these two subtracted trials, that on the one where you changed your mind, you were less certain and had your motor system less tuned. Because there's not only the uncertainty that we put in our stimuli, there's also the uncertainty that is added by your own brain, and you're probably aware of that. Okay, and if you then look at this difference curve for all the subject, and we look at the average of this, R3, this bit and that bit, and the average of this bit and that bit, what you get is that especially for left to right changes, you see a massive reduction by the change of mind in the R3 window, which is probably confidence that we're looking at. So, conclusion 2b, CNS provides information from an ongoing process to the motor system. The motor system is pre-tuned. The pre-tuning results in faster completion. And if you show a change of mind, then you probably also show reduced confidence in your EMG. We're currently thinking about tricks how we can actually tease apart confidence from really the implementation of the change of mind, because that's pretty hard. And the trick that you can play there is look at when in the trajectory do you actually switch over to the other side, because late changes of mind should have different levels of EMG activity or reflex activity than early changes of mind. But it's only 7-8% of trials that are change of mind, so it's a bit tricky on the amount of data you have. Okay. This is also decision making, still related. This is the last one I'm going to do. That's the competition between reach targets within fast vasomotor pathways. So this was a joint. So there is a collaboration between Western University, Canada, and the Donnes Institute. And so Chow was a PhD student of Brian Cornell at Western, and they are interested in something called SLR, stimulus locked responses. It's EMG. I'll explain you in a bit. So this figure, every movement scientist should know. If you have to make a reaching movement with your elbow, Dinant has done these very fast movements, then I should have used your figure, sorry. Then if you have to make a flexion, then you first get activity of the agonist, then the antagonist, and then the agonist to fine tune the thing. That pattern we all know. But if you look really, really carefully at EMG data, then you also find another response that is not correlated with the reaction time, but is nicely aligned with the onset of the target, especially visual target. So here I show you some data from Chow. So at T0, we present you quickly, unknown to you or whether it's going to be left or right, a target. And what you then see is 100 milliseconds after the presentation, you see a blip in the EMG activity, whereas the voluntary bit comes much later. And if I present you a visual stimulus to the right, and we're looking again at pectoralis muscle, to the right, where pectoralis should turn off, then we see a dip showing. And this is pro-reaches. So the instruction is, if you see something to the left, reach to the left. If you see something to the right, reach to the right. But you can also give the anti-reach instruction. If you see something to the left, go to the right. And then what you see is that in the voluntary bit, you actually do go to the right. But in the SLR bit, in the early window, you see a blip that looks very much like the voluntary, like the pro-reach, but a little bit reduced, and the same holds here. Okay, so you essentially see in the voluntary bit, the red and the green are the same, red here, green there, but in the involuntary bit or the visually evoked bit, you see that the stimulus determines the response. And this is probably reticular spinal tract and has probably to do with orienting responses. You find it in proximal muscles, and you find it especially in the neck for head rotations. So this we call SLR, stimulus locked response. It's visually induced orienting, and it has a different neural circuit than the voluntary response. That's the hunch at the moment. Okay, but what we were interested in is, what if I present you two targets? Do you then get a doubling of this SLR? And there's a big discussion in the motor control literature whether we express averaged motor programs, or whether that really is averaging at the neural level, or whether that is behavior that is optimal for the task. Sometimes it's good to go through the middle. If you don't yet know what to do, better wait with your decision and take something intermediate. So we think we can have a window on whether it is true averaging at a neuronal level. So is there competition between the two SLRs if I present you with two targets? Is that if that competition is not resolved, do we then get averaging? And at what level does that averaging take place? Again, pectoralis, we presented our subjects with 12 targets around the circle from a central position. They never saw all these dots together, only 2 of them. Normally, what you get is, if you have to go to the left, you get an SLR upwards and the voluntary, and if you get a target to the right, a downward SLR and an EMG downwards. Note that this is all with a background load on the muscle, else you do not get a reduction in muscle activity. And then what you can do is you have EMG responses for all these targets, and you compute the activity in this time window and plot that as a function of direction. And then you fit a sinusoid through the log EMG, and that we call a tuning curve. You can build it for neurons, but you can also build it for muscles. That tuning curve has a peak, has an amplitude, and we can do that for the SLR epoch, that is here, or for the movement epoch, where the voluntary EMG starts. And they look very similar here, okay? And all the dots are individual trials of a single subject. Now, if you compute the amplitude of the SLR window versus the movement window, they differ. It's bigger for movement, but the preferred direction does not. So where the peak expression of EMG activity is, it does not differ between SLR epoch or movement epoch. So this visually evoked response or the voluntary reaction to that. Okay, now we want to know, do these tuning curves actually change if there's another target that you did not choose? So we have a free choice. You're presented with two targets and you have to react fast, and we don't care whether you hit this one or that one. And we did it with 60 degrees separation for all possible combinations, 120 and 180. And we had a couple of hypotheses. Suppose that the SLR is not affected by that second target at all. There is no competition, you just go for one. Then essentially, you only walk the path for the chosen target. That is stimulus 1, you get a tuning curve for stimulus 1 that generates a motor command, and essentially your tuning curve should be the exact same as a single target. Or you do something called spatial averaging. That would mean you see two targets, and in first instance, your neuronal system says, well, I see the average of these two targets, so that's this one. So you see stimulus 1, stimulus 2, you average the two, and in essence, if I have a 120 degree separation, the tuning curve should shift by 60 degrees because you should go in the middle. And if the distractor is to the left, clockwise, then you should go in the other direction with your tuning curve than if the distractor is counterclockwise. Or maybe it's motor averaging. So there you again have the two stimuli, but you convert the two stimuli in their respective tuning curves, then generate the motor commands, and only then average them. And that means that the peak of the curves remains at the same spot, but they collapse in magnitude. Okay, these were the three hypotheses. So let's first look at a couple of trials. SLR 120 degree choice trials, and the same reach direction, different target configuration. So we reach forward, there's a distractor counterclockwise, or you reach forward and there's a distractor counterclockwise. If you look at the EMG, then what you see is that you get opposite SLR responses. It's kind of funny because it means that this one increases the SLR and that one decreases the SLR. So there's some sort of averaging going on here. So now we compute for the 120 degree choice targets again the tuning curves, and now we have a tuning curve for a distractor counterclockwise or a distractor clockwise, separate tuning curves, and we see that they shift relative to the original black one, and they may collapse a bit. Single subject is. So we had these three models: competition resolved, spatial averaging, or motor averaging. Well, this one cannot be. That's out of the question. These two can still be. So now we have to look at, okay, does the magnitude actually collapse? So for that, we look at the 60, 120, and 180 degree apart targets. And we compute the change in preferred direction for the 60, 120, and 180. So the dashed lines mean that you do a full averaging. You don't do that, but you do some averaging. And here as well, but not as much. And if you would go all the level up to here, then you would have completely averaged. And if you look at the amplitude of the tuning, then we see a decrease. Now, the spatial averaging model says you should not see any decrease in the tuning curves. except for 180, because there the tuning curves will cancel each other. So the prediction from this model, spatial averaging, is the red lines. That cannot be, so it must be that one to some extent. But we have a problem, because this model says 60-degree shift, but we never make the full shift. So therefore, we came up with an alternative, post hoc, I immediately admit, a weighted motor averaging. So what you do, stimulus 1, stimulus 2, sorry, this is the standard motor averaging, in which you weigh both stimuli equally heavily. But what you can also do is say, like, well, I weigh in the chosen stimulus, the tuning curve of that stimulus, more heavily than the non-chosen stimulus. Then we do the averaging again, because what happens then is that you can play around with how much shift of the tuning curve you get, because this one counts in more heavily than that one. Now, obviously, we could have done that by optimizing weights on them, but we actually started from data. So a single target tuning curve looks like this, but we know from the past that if your SLR is large, your reaction time is short, and if your SLR is small, your reaction time will be slow. So what we did is we did a median split on our reaction time data for the single target trials. Fast reaction times gives me this, slow reaction times gives me that. So what we see is that the preferred direction of these two tuning curves does not change, but the amplitude does. And what we do now is we take the slow reaction time RT for the non-chosen targets and the fast reaction time for the chosen targets. And if you do that, this leaves a model with no free parameters. If you do that, then these bars are the data, and this is the prediction of that weighted motor averaging model that was purely data driven. It was not optimized, but we capture the responses, and the red one was the original motor averaging. Yep, the motor and the weighted motor, and this one does much better. Now, then the question is, if you do averaging, do we see something of these averages? And yes, you do. If you look really, really carefully at the kinematics, you see this is a single target distribution of initial reach direction. This is if you have 60-degree targets with distracted to the left or to the right, you see a tiny shift of the curves. And if you put the targets further apart, the curves shift further as well. And if we plot that as a function of time or reach percentage, you see that initially they're far apart and they come closer. And if you then look at the tuning of the movement epoch, you see actually a negative shift of the preferred direction. So instead of that they average, they're pushed apart. And we interpret that as a compensation mechanism. Somehow the brain already knows that it was attracted by the distractor and is going to compensate early in the trajectory to make sure it gets to the target. Okay. So this is a summary of that. SLR shows competition as a weighted motor averaging. Preferred directions, shifts, and amplitudes change. But in the movement, what we see is the amplitude doesn't change in the EMG, but we do see some repulsion in the EMG. But that's a correction for the averaging from the SLR. So SLR provides a window on low-level averaging processes, which may add to the debate on whether averaging, as we see in reach trajectories, whether that is neuronal or really a deliberate strategy of the system. Okay, this I don't do. I have to quickly go a few slides down. So what have I said? Computational models help interpreting vestibular aging. We hope at some point to make clinical use of that. There's no clear watershed between perception and action. We really leak information into the motor system, which makes it easier to release an action early on, even though we're not sure yet. Motor averaging is at least partially hardwired, and the other one I didn't talk about, that's for another time. That's it.
Thank you very much, Luc. Cleverly designed experiments, cool experiments and analyses. And I always thought that studying brain activity was complicated, but I think this is quite a challenge. We are a little bit short on time, I think, but probably there's a lot of questions. Maybe it's a good idea if people that have a question to ask, just put their name in the chat.
There.
I think there's
Saw your hand, Bernadette.
a lot of processing going on.
Can I ask my question?
Yes, of
Yes.
course.
Then the rest can process.
Thanks, Luc. Very nice work. I have a question about the second part of your presentation, so the decision-making experiment.
Mhm.
And I was wondering whether you observed any biases in the decision that people made induced by your perturbation. So if you give the perturbation, were people more likely to then actually go for the choice in line with that perturbation? So that would suggest that the motor system does not just receive an update of the decision-making process, but that it can also influence the decision that you're going to make.
Thanks. That's a good one. First, the perturbation was always the same in our case. So always in the same direction. So if there was a biasing effect, it would always be the same biasing effect. We have problems with bias. So the model that I described to you essentially does not capture bias, and we're now implementing biases into that model, because in a diffusion model, you can introduce bias as well, especially in these change of mind experiments. So yes, we have a problem with the bias. I cannot answer your question from my data. I know that people have played around with that you can indeed manipulate the choices of subjects by, well, giving the go cue in particular ways, so that you can bias the system. In essence, the system makes a weighting between the evidence, which is not perfect, and cost. So if I give you a perturbation that goes far away from what you think is correct, but you're not 100% sure, then you decide for the less likely option, but with less effort. So somehow you weigh these two. Does that in part answer your question? We haven't done it.
Yeah. I'm familiar with the studies I think you're mentioning. I was wondering whether you observed anything in your data.
No, we haven't done the perturbation to do it that way.
Yeah, okay.
But we see biasing effects that we do not see if we, so we've done the same experiments without the perturbations, and then that bias is away. So the perturbation has an effect on the choices.
Yeah. Interesting.
We try to manipulate the perturbation in such a way that we don't bias. But that's tricky. Yeah.
Thanks. Yep.
You're welcome.
Any other questions? I have a bit of a personal interest question. So you're saying that you are a fan of studying behavior only versus studying brain activity. And in my screen, you are next to Bernadette, who's doing, I think, more or less the opposite. So I was wondering if you could evaluate on that.
So I'm not going to judge for Bernadette. But we have a massive imaging center a couple of doors further. And oftentimes they attribute things to the brain and I'm like, that's already solved in the periphery. So that's why I say I want to look at behavior first before we go into a scanner. And I know I bring that a bit blunt every now and then, but I think that's the only way here to say that in a blunt way. Because there's a massive focus on the brain. People here in Nijmegen don't know where muscles are. That sounds silly, but they have never had any biomechanics. I had one PhD student, and she did stuff that required biomechanics, and I thought, she will learn it on the fly. That doesn't work. I should have sent her to Amsterdam to take a couple of courses. But so that's why I am sometimes pushing, like, look at the periphery. You can learn a lot from it. So, does that?
Well, I fully agree, but I'm curious.
Yeah, I was trained by you.
About reactions from Bernadette or maybe Andreas, if he's still around.
He left, I think.
He left.
Okay.
Yeah, well, what can I say? I mean, of course, both can give you information, right?
Yes.
And you can also still look at traces of motor preparation in the EEG or the MEG signal. Yep. And I would guess that if you were to do such an experiment, you will also see a lateralized beta desynchronization towards that choice that you're going to make already during the decision period.
I'm pretty sure that information is actually out there.
Yeah. The nice thing about your experiment is that you do this perturbation, I guess, and that you can also dissociate the preparation at different phases or different stages of the nervous system, right? So the early, yeah, that's quite elegant.
We're planning, if you don't scoop me, what we're planning on is actually to try to use EEG and actually use corticomuscular coherence.
Oh, nice.
If you believe that these reflexes are essentially building up a super fast highway to that muscle that you need later, then you might hypothesize that your corticomuscular coherence should increase over the deliberation process. The more certain you get, the more corticomuscular coherence, the higher corticomuscular coherence you get. But that's a hunch. And obviously, ideally, you should go to an MEG system, but they don't like movement. So yes, we're going to see whether that works. But because the experiment is fairly easy to do, the analysis is a pain.
Yeah, nice. And I think people have also tried something similar with TMS, right? So you can also give TMS pulses basically at the different time points that you now used your perturbation.
Julie Duke has done that. But then so that's a different technique. The reason that I would want to go to corticomuscular coherence is that now I have a single measurement from every trial, which is a pain. That's why I need 3,600 trials to get something out. But if you would use corticomuscular coherence, you have a time trace on every trial. And that's the problem also with the TMS. You only have one measurement every trial. You have one state, but you want a change of the state in that trial. That's why I would want to go for something that is continuous.
Okay, but before we get too technical, I think it's good for the research master students to see that there's more to just studying the brain. Using measurements of neuronal activity. Very nice. For the sake of time, I suggest that we close the meeting by thanking Luc. So I don't know how this works. I thought it was a really cool presentation. And people that want to hang on to have a little bit further discussion, please stay. I think that's so the people are leaving. Have a good night. People are staying. Looking forward to the discussion.